So good morning, everyone. Welcome, and let's start today's session with Marcel Gurdia. And Marcel will speak about symbolic dynamics and oscillatory motions in the three-body problems. Please, Marcel.
Okay, so thank you.
Of course, we love you as well.
So thank you for the invitation to be here. It's a great pleasure to be again in Italy and first time in Varese. So that's joint work. Let's see if it works. Oops, yeah, with Pau Martin, Jaime Paradela, and Teresa Ara, all three also at UPC, like me, in Barcelona. So that's a talk in transversal mechanics, I would say, in a very classical problem. So let me still start by putting the model that you all know, but just to fix notation and to fix the setting. So essentially, in the whole talk, I'm going to be in the three-body problem, most of the time in the planar three-body problem. I will switch slightly. So I have three bodies of positive mass, m0, m1, and m2, which move in the plane just by the law of gravitation. You all know the model, so it is model here, given by Newton laws. So on this model, I want to address two problems, which you'll see that they are very much related. One is to see if such model has chaotic motions, and I'll be more concrete in a minute. And then, that's a general problem in dynamics. And then I want also to study what we'll call final motions for the three-body problem that I'm going to also define in a minute. Okay, so that's the two topics that you'll see that they are very much connected. So chaos, well, the one you can guess. For me, chaotic motions, I mean that I will have the shift on the space of symbols. Here, for me, it's going to be more important to have a shift on an infinite symbols, say, space of sequences. And I want to embed this dynamics in the three-body problem, okay? Or what we say usually to build small horseshoes for the three-body problem. Even if it's like a very classical question, there are not so many results, and I'll mention them later, okay? And more concretely, I want to construct hyperbolic sets whose dynamics is conjugated to the shift, okay? So that's the first problem. The second one is what we call final motions, and this goes back to Chassis in the 1922, who proposed the following. Say, since the three-body problem, as you know, it's a mess, it's a very hard problem to analyze, let's just ask a simple question. That's which possible behaviors this model can have when t tends to infinity, okay? Look only at orbits which are defined for all time. I mean, some go to collision, forget about them. So just take orbits which are, say, complete, defined for all time. And I want to classify to see which options there are of behaviors for these orbits when t goes to infinity, okay? Either, say, 2 plus or, 2 plus or minus infinity. So then Chassis proved that there are 7 options, and that's it, okay? So if I call Ri the mutual distances between bodies, then we go through these 7 options. Say all bodies could go to infinity with positive speed. All bodies could go to infinity with 0 speed, asymptotically, okay? And these are called hyperbolic motions and parabolic motions. Here, the plus and minus means for plus infinity or minus infinity. Orbits can be bounded, and you all know what this means. There are these three which are, say, combinations. So some bodies could go to infinity with positive velocity, others with 0 velocity, and this is called hyperbolic parabolic. Some could go to infinity with positive velocity, whereas others stay bounded. And this is, sorry, I don't know in the middle. It's called hyperbolic elliptic. Or some could go to to infinity with 0 velocity, others bounded, and this is called parabolic elliptic. So these are the first 6 types, and then he proposed a 7th type that he couldn't prove that it existed, but that he couldn't rule out that it did not exist, okay? And that's the one in red, which are motions which he called, or we called, oscillatory. So those are motions such that the limb sup of the mutual distances is infinite, whereas the limb inf, it's finite. That is, my bodies separate, get back close together, they go farther away, they get close together again, and so they oscillate between infinity and a compact region in phase space, okay? So they are in red first because those are the ones that I'm going to study in this talk, so to speak, but also because they are particular, in a sense, compared with the other 6, okay? Why so? Well, one could take the three-body problem in the limit when the, say, two masses go to 0, okay? So a very big mass and the other two in the limit of very small mass. Then in this limit, these two bodies don't see each other. So in this limit, the three-body problem becomes two uncoupled two-body problems, okay? So it's integrable because, I mean, we just have the classical Kepler problem. And we all know that in this limit regime, one can place the bodies, one must place the bodies in conics. So either in ellipses, in parabolas, or in hyperbolas. And then if you go back to this, sorry, oops, I messed up with the, if one goes back to this list in this limit case, one sees that actually this would correspond to putting in this limit with two masses equal to 0, to put all bodies in hyperbolas, these bodies in parabolas, these bodies in ellipses, and these three, well, putting one in parabolas, one in ellipses, and so on. So all these first 6 cases, they do exist for these two-body problems, okay? I mean, they are, say, I mean, they can be seen in the integrability of two uncoupled two-way problems. Whereas this, oops, again, sorry, I'm gonna mess up with, so this 7th case, in a sense, is genuinely three-body problem. This does not appear in this limit case of two-body problems. That's why Chassis, obviously, I mean, could prove that these first 6 existed, and he was not able to see, I mean, he guessed that this 7th should exist, but he couldn't prove it, okay? So this was in the 20s. And then Chassis, and then one more comment. Obviously, in this limit, if the bodies are on parabolas, they are on parabolas for all time. So what happens when t tends to plus infinity is the same as what happens to t tends to minus infinity. Or in further ways, what happened in the past determines what passes in the future, okay? So when Chassis did this analysis, he posed 2 questions. First, as I've mentioned, whether this 7th case exists or not. And second, whether one can combine different past and future motion. So can a body be in the past bounded, and in the future parabolic, or I mean, any possible choice of past and future behavior. So since Chassis, there have been a number of works, not from the 20s, but from the 60s, 70s. But typically, they deal with the three-body problem. That is, I take one of the masses equal to 0. So that's already non-integrable, but it's, say, simpler than the full three-body problem. And typically, the choice of masses of the other two, or of the 3, if it's for the full three-body problem, belong to a quite narrow range of parameters. I mean, the choices are very particular, okay? So the goal here is to analyze these 2 problems for a big set of masses. I mean, not to impose conditions on the masses. So the first result in the, say, answering these 2 questions by Chassis was in the 60s, and this was by Sitnikov, who considered a very particular model that is now called the Sitnikov model, which is as follows. So it's this picture here. It's a restricted model, so one of the bodies has mass 0, and it's in the space. So we take the first 2 bodies with equal mass, so say 1/2, okay, and then they do ellipses, which are, say, centered at one focus, and they are, say, symmetric because it's the same mass. And then the third body is put in the vertical axis going through the center of mass, okay? So this axis is invariant because these 2 ellipses are equal, so the forces compensate, okay? And he analyzed these questions in this model. So here he proves first that there are motions which are oscillatory, and here this means that the body goes farther up, but then goes back and goes farther down, much farther down, then it goes up. Oops, I lost the. So keep going up and down, going farther away, but always crossing the center of mass. Okay, so he proved that such motions existed, and that he could combine past and future quite freely. Okay. Some years after, in 73, Moser reproved. I mean, I never saw the proof by Sitnikov. I think it's only in Russian. So, but I mean, I don't know how he proved it. But I mean, what now it's say the most common proof is the one by Moser in 1923 in his book Stable and Random Motions, where he considers again this problem, and he proves the same, relating these behaviors to chaotic motions. I mean, he proves this behavior by building a Smale horseshoe, a hyperbolic set for this model. Okay, and this is actually also, I would say, one of the first proofs of, say, a Smale horseshoe in a physical model after Smale. Most of the results in the area afterwards, I would say, follow in some sense or another the ideas that Moser developed that I will mention later, and I will also use them here today. Okay, so afterwards there's been quite a number of works. I don't want to go into them, but first for the restricted planar circular three-body problem. So three bodies on the plane, one body of mass 0, and then the other two doing a two-body problem on circles. Okay. So for this model, this has been proved. Then there are other works I'm not going to comment. Many of them following, say, what we could call geometric methods. So, so close to what Moser proposed. And then a rather different one by Kaloshin and Galante, which uses probably matter theory, which is a very different nature. Still, this is all for restricted models. Okay, so one mass equal to 0. If one goes to the true model, say to the true three-body problem, so all three masses positive, as far as I know, there are only two results, both for oscillatory motions and for chaotic motions. So even if chaotic motions, I mean, it's a very critical problem. As far as I know, that's the only two that deal with this problem for the full three-body problem. So the first one is by Alexeyev, which is actually before Moser, so it's from 69, who considered a Sydnikov-like model, so two equal masses, and the other very small. Okay, so this can be seen somehow as a perturbation for the Sydnikov model. So again, a quite strict assumption on how are the masses, and also it's very symmetric. So one can reduce drastically the dimension, and that's not a minor thing. You'll see it later. So even if obviously that's before Moser, I mean, one could reprove what he did using Moser ideas. Okay, and then in this model, one can prove again that motions that there are motions which are oscillatory, and also one can build hyperbolic sets. Still, again, with as I've said, with a quite strict choice of masses. Much more recent is a work by Rick Mockel, who considers, say, an sort of big set on masses. I mean, big, but I mean not generic, but I mean it's not, say, like very narrow range. And then he proves the existence of oscillatory motions. And he proves, if you want, a weak form of chaotic motions, meaning that he proves semi-conjugation with a Smale horseshoe, so semi-conjugation to symbolic dynamics, which certainly does not imply that there are, say, Smale horseshoes as such. I mean, there are no hyperbolic sets, but I mean, still, it indicates some sort of chaotic behavior. And this is of very, say, different nature from the things I've mentioned before. I mean, this goes through passing close to a triple collision. So as far as I know, these are the only two results we deal with, in some sense, chaotic motions for the full three-body problem. So before going into presenting what we've done, let me mention another problem, which is also important in the field, which is not about the existence of different type of final motions or the existence of motions which are oscillatory, but on the, say, abundance of these motions, that is, on the measure of such motions. Okay, so what's the question? So take any past final motion you want and combine it with any future final motion you want. So let's try to see what's the measure of this set. Not, I mean, more concretely, whether this set has positive measure or zero measure. Okay, as a way to classify whether it's say an important set in the Fisher space or not. So it turns out that put any combination you want. So for any combination, it is known whether this set has positive or zero measure, except for one combination. Okay, and this one, it's the motions which are oscillatory in the past and in the future. Okay, so combine any one of these 7 options. We know for all of them whether it has zero measure or positive measure, except for the set of motions which are fully oscillatory. Okay. So there's a conjecture by Kolmogorov and Alexeyev. It's not clear the origin. I mean, there are like different sources, and they're not clear. I mean, who posed it first anyway? But I mean, it goes back to this to them, which conjectures that the Lebesgue measure of this set should be 0. Okay, but that's wide open. I think it was in the conference for this 60th birthday by Alexeyev. Arnold called this the central problem in transfer mechanics, but it's a wide open conjecture. I wouldn't say even whether people believe that's true or not. I mean, it's quite open even to guess what should happen. Still, what we know is say that they are abandoned, these motions from PV1 from the point of view of topology. So Kaloshin and Gorodetsky proved that the Hausdorff dimension of such motions, or motions which are oscillatory in the past or in the future, it's maximal. Okay, so this set has maximal Hausdorff dimension, and this is both for this Sydnikov problem and for the just planar circular three-body problem. Still, I mean, I don't want this slide to give the impression that the issue of existence is closed, because I mean, even if that's known, this is for a rather narrow range of parameters that's proven. That's the range that, say, Sydnikov used. Okay, so still the proof of existence for a wide set of parameters, it's wasn't that known. So let me present the two results that we've done. One about final motions, and the other one about chaotic motions. So first, about final motion. So consider the three-body problem with 3 positive masses. They can be anything you want, as long as the first 2 are different. Okay, so there's only this condition. Then we can prove that we can combine past motion and future motion among this set here. So motions which can be either oscillatory, either bounded, either parabolic elliptic, that is, one pair is bounded and the other one is going to infinity with zero velocity, or hyperbolic elliptic. So one pair is bounded and the other is going to infinity with positive velocity. Okay, so among these 4, we can combine all possible past and future behaviors. So in particular, we can prove that there are motions which are in the past and in the future oscillatory, with essentially all choices of masses. Okay, as long as we have these conditions here. Okay. So obviously, among the 7 cases I've put, not all happen at all levels of energy. So at negative energy, that's what we consider, these are the only options that could happen. So we can combine all possible options in negative energy regime. I say almost because obviously we could, I say almost because we could combine, say, PE2 with PE1. I mean, we could have exchange of which ones are bounded and which ones go to infinity, and this we don't do. But as long as types of motions, we have all possible combinations. Okay. What's the? Let me try to make a picture. What's the idea that one should have in mind is that we have 2 bodies doing close to circular motion, and then so these are, I mean, they keep bounded for all time, and then there is a third body which is gonna which can do whatever you want. So this third body can stay bounded, can go to infinity with positive velocity, with zero velocity, or be oscillatory, meaning that it goes far away, it comes back, far away, it comes back. Okay. Okay. So that's the first result. So let me go to the second one, which is about chaotic motions. So again, same assumption. So consider the planar three-body problem with 3 masses positive, as I mean, with any value you want, as long again as the first 2 are different. And then the node by phi of t, it's flow, and actually the flow, once you have reduced the model by translations, by rotations and everything, I mean, you have to kill first integrals. Then I can construct a Poincare section for this flow, and define an induced Poincare map, so that basically just to make it sure this Poincare map has an invariant set which has, whose dynamics is conjugated to the usual shift of infinite dimensions. Okay, so just say that this model has chaotic motions for essentially all values of the masses. Okay. So in particular, as a consequence, we prove that the three-body problem, has invariant sets with a positive topological entropy, which even if it's, everybody knows this should be true. There are not many proofs about that. Okay, and this set is hyperbolic. Sorry, oops. Once the model is reduced by all first integrals. Okay, so we build a true hyperbolic set whose dynamics is conjugated to the shift. There are further results about chaotic motion, which are not related to the setting I'm giving, but as far as I know, they are again all for the restricted three-body problem. So with one mass equal to 0. Okay, so for the full three-body problem, there are only the two I've given before by Meckel and by Alexeyev. So here, when we conjugate to the shift, or when we conjugate, when we build a set which is homeomorphic to the space of sequences, what is this, say, labeling in three-body problem, or how can we see this chaotic behavior? So let me make this picture. This is cheating quite a bit, because this one should be done. This should be done once you have reduced by all first integrals, not in the full three. But anyway, let me cheat. So that's the picture I've put before. So we have two bodies doing close to circular motion, and then this third body which is going far away to infinity and coming back. Okay. Then I put this section which is transverse to the flow, and then I'm gonna look at this Q2 each time it hits this section. Okay. Then between two hittings, these two bodies have gone. Have done certain revolutions. Okay. So this number of revolutions is gonna give me the number, say, from the sequence in the shift, like in the Smale horseshoe. Okay. So more properly, let me call nk the number of complete revolutions between these two, say, almost close to circular bodies between two consecutive hittings of Q2 with pi. Then there's some large number L. Obviously, it takes a long time to go back to this section. So that take any sequence in the space of n power z, then there is a solution of the 3BPs such that the number of revolutions after, between hittings is this L plus whatever you choose in the space of sequences. Okay, so that's labeling, say, the chaotic behavior. Okay, so let me give some idea. So I have to. Okay, fantastic. So let me give some ideas on the proof of these two theorems, which they are proofs, say, together. And for this, let me go back to the ideas by Moser in his book Stable and Random Motions, and then let me explain how we implement, say, the ideas that he proposed for this Tinnikov model to the full three-body problem. Okay, and you'll see that there are say deep changes from one model to the other. So a key point here is that the Tinnikov problem is a 1 degree of freedom Hamiltonian plus time dependence, so it can be reduced to a two-dimensional Poincare map. Okay, so it's, say, of the lowest possible dimension where one can see chaotic motions. Okay, and this helps, and you'll see why in a moment. So what Moser realized, or actually before him McGehee, is that one can see infinity as a fixed point of this model. Doing a good change of coordinates. Okay, so one has a fixed point at infinity, and one can prove, and this was proven by McGehee in '72, that this fixed point at infinity has stable and unstable invariant manifolds. Okay, that's not obvious because this point, it's at infinity, it's not hyperbolic, it's parabolic. I mean that when you linearize the Poincare map around this point, you only see the identity. Okay, so you need to look at the nonlinear terms to see that actually it has invariant manifolds. This is not I would say a minor thing. This has implies changes in the dynamics. For instance, well, one knows that when one has a saddle, orbits in the invariant manifolds decay exponentially to the saddle, to the fixed point. When motion is, say, here is parabolic, the convergence of the orbits in the invariant manifold is power-like, but not exponential. Okay, and this has some effects. In the dynamics. Still, one can prove that that this fixed point at infinity has invariant manifolds, and they are regular with parameters. They are nice in a sense. And then step 2 is to prove that these invariant manifolds intersect transversally. Okay, and this, in the case of Sitnikov, this can be done by classical perturbative techniques, what we call Penlikov theory or Poincare-Penlikov theory, which gives us transverse Hawkinic orbits to infinity. Okay. Now we know by the classical Smale theorem or Birkhoff-Smale theorem that if one has a fixed point in a map with transverse homoclinics, it has hyperbolic sets, horseshoes. Here one has to work more because this P is not hyperbolic but parabolic. Okay, but still, and Moser did that. Moser proved what we could call a parabolic lambda lemma. Okay, so again, an analysis of how is the dynamics close to this fixed point at infinity, which at the end means that one can implement the proof of the Birkhoff-Smale theorem. Okay, so yes.
Which are the parameters? The rate of convergence to the parabolic
yes.
point depends on which parameter?
No, the convergence is t minus 1/3. This is fixed.
Okay.
This doesn't. And this comes basically also, for the two-body problem, actually. It's a very rigid. So one has, once one has this parabolic lambda lemma, one can say implement the Birkhoff-Smale theorem, whatever you want to call it, isolating blocks or say vertical strips and horizontal strips. The usual way, or windows that one proves the Smale theorem, putting rectangles and seeing that they are well aligned under the map. Okay, here is important to have an infinite number of strips which accumulate to the stable manifold, and then that when you apply the map, they all get well crossed. Say, why? Because then, if you obtain an orbit which follows strips which are much closer to the invariant manifolds, if you are closer to the invariant manifolds, you are getting closer to this fixed point, which is at infinity. So these motions are postulatory. You need to get as close as you want to the invariant manifolds to be postulatory. This would only lead to semi-conjugation, but then you have to put, say, confields, conditions to see that this set is hyperbolic, like in the usual way in hyperbolic theory, to build a hyperbolic set, which is a Smale horseshoe. Now, as I've said before, that's the true picture, meaning that we are in the plane. And a key point here is that the Sitnikov model can be reduced to a two-dimensional map. Okay, and actually the same happens for the two other models where we have, say, similar results: the restricted planar circular three-body problem and the Plexev model. Okay, so reducing to a two-dimensional Poincare map, it's a very important point in the proof. So what happens if we go to our model? Yes. Yes.
So, why do you need to get a hyperbolic set? Don't you get like a topological
Yes, to prove that there are that there are motions which are postulatory, it's enough to prove that that it's topological horseshoe. I don't know. I like to prove like to implement, say, the classical Smale-Birkhoff theorem in this model, but that's not important to build motions which are postulatory. So how can we say implement, if you want, this Moser approach for the full three-body problem? Okay, so if one would do the same, which is, let's reduce by the classical first integrals, let's consider a Poincare map, then we go from a two-dimensional Poincare map to a four-dimensional Poincare map. Okay, so we increase the dimension by 2, and that's not a minor change. Why? Because if before, for Sitnikov, at infinity, we had a fixed point, which was, say, isolated and had invariant manifolds. Now, at infinity, what we have is a disk of fixed points. Okay? Sorry. A disk in R2, a 2D disk of fixed points. Or what's to say that at infinity, at infinity now, what we have is that dynamics is the identity, okay? Which obviously, if you want to build hyperbolic sets, that's clearly your enemy. I mean, this couldn't be more degenerate, okay? So close to infinity, you are extremely close to the identity, okay? So that's a clear, say, difficult. I mean, and this is even true if you want to prove that. I mean, like a zero horseshoe. I mean, even if the set is not hyperbolic, I mean, to build a horseshoe, I mean, this is obviously a clear problem.
I don't understand in this case what it means being close to infinity, because in the case of Moser there is some change of coordinate here. It's more complicated, so I don't see.
Yeah, it's not. It's the same thing. So we had these two bodies doing circles, and then this third body. Oops. So I mean, you parameterize this body in polar coordinates, and that's your radius. And then it's this radius, the one that you send to infinity. And then the angle actually is putting dimensions into this disk. So one can do the same trick as in Sidikov, but for the radius of the third body. Yeah, thank you. So so this was the first, say, difficulty that we have. Second is that we want to give results for essentially all values of masses, okay? But they've said that a key point in the proof is to see that the invariant manifolds of infinity intersect transversally. And typically, we only know how to do that if we are close to interval, okay? So even if we choose any value of masses, we want to be in a close to interval regime, okay? And that's obviously, again, a difficulty that will apply. Yes?
All values of axis, but always with M0.
Always, yeah. I mean, I can comment at the end if you want about this condition. I mean, why does it appear? Yeah, okay, I can comment now. So these bodies do close to circular motions, right? So I mean, imagine then if the masses are different, you have basically this picture, right? One body here and one body here. But if the masses are equal, well, what you get is this, right? Because the radius depends on the masses. This seems a very naive, a not so important change, but it is. Because here you have a period 2π, and here you have period π, right? And this transition is a nightmare. I mean, here one sees many bifurcations, exactly when one wants to analyze the transversality of invariant manifolds. And I mean, maybe we could handle that, but this is a nightmare. So we avoid this case. So that's the reason. I mean, I'm sure all this also happens for the case of, without this, but the proof should be different. And that's why we avoid this case. So again, as I was saying, we need to set up a close to interval regime, even if, for all values of masses. So how much time do I have now? Sorry.
10 minutes.
Okay. So let me put a scheme of the proof, and then I'll mention what happens in some parts. So as happens for, say, for Moser or for Birkhoff, there are two parts, say the global one and the local one, and this is the same. So we need to analyze the transversality of the invariant manifolds of infinity. Analyze this transversality by means of what we call the scattering maps, and that's an object that Marian defined yesterday, and we will also have to use it. And then this will lead to analyzing what we call global maps, so the dynamics along the invariant manifolds. On the other side, we have to analyze what happens close to infinity, like in the neighborhood of this disk of fixed points. And there we have to do what we call a parabolic normal form and a lambda lemma, which is going to describe the local dynamics close to infinity. Okay, combining these two columns, one can somehow implement this idea of of Smale, of Moser, of having these strips, vertical and horizontal strips, now of dimension 4, because we are in a 4D map, which will lead to both oscillatory motions and say Smale horseshoes, or to symbolic dynamics. So I won't talk much about, none about that, but let me give some ideas of this first column, okay? So on how are the invariant manifolds and how is the dynamics along these invariant manifolds. So I've said that to analyze this, we need to be in a closed to interval regime. So what's going to be this interval regime? So we want to put the third body, Q2, very far away from the other two. Okay, so the picture is the one I've done 1,000 times, so, but now let me put it more exaggerated. We have two bodies doing a tiny radius compared to extremely far away third body in a parabola. And this distance is going to be my perturbative parameter. Or if you want the inverse, it's going to be very small, and that's going to be my parameter of perturbation. Why is this close to integrable? Well, because if you would be placed here, and you would look at the other two bodies, at first order, you would only see one body by the center of mass. Yeah. So, so from here, you see just one body at the center of mass, plus errors, which come from the fact that they are very close to each other, but they are different bodies. Okay, so that's a close to interval regime. So what we have is two uncoupled Kepler problems, one here between these two bodies, and one between this body and the center of mass, plus some coupling, plus some small perturbation. So that's fine. Now this creates a problem, okay? Because this makes this problem have two time scales, okay? Why? Well, we know that the Newton law of gravitation depends on the distance. No, I mean the farther you are, the quicker it is. So since this body is very far away from the other two, the motion on this parabola is extremely slower. I mean, it's much slower compared to the motion on these two bodies, because they are close to each other. So we have slow dynamics on the parabola on Q2 and fast rotation on the first two bodies, okay? And this makes, say, life harder because when now we want to analyze the transversality between the invariant manifolds, we see that this transversality is exponentially small with respect to our parameter, to this inverse of the distance. So it's smaller than any power of the parameter, okay? Which means, I mean, and this phenomenon is called usually exponentially small splitting of separate traces. Why? Well, because that's what happens typically in systems which are conservative, which couple fast rotation with slow motion on invariant manifolds, as happens here in this model. So in this setting, I mean, since this splitting, since the angle between these invariant manifolds it's smaller than any power of your parameter, the classical perturbative techniques that were the ones used by, say, by Moser, for instance, what we call Pentecost theory does not apply. One has to use other techniques, okay? And here, say, the seminal work to analyze such phenomenon goes back to the study by Laszlo in the 80s for the standard map, which tells you that to analyze this transversality between invariant manifolds, one has to look not at the invariant manifolds for your, say, for your real problem, but you have to complexify your problem and analyze these invariant manifolds for complex values of the parameters you use to parameterize the invariant manifolds. So one has to, I mean, obviously, I mean, after the 80s, there's quite a number of works in this field, so I'm not going to cite them. But we, say, use these ideas. Typically, they've been used for lower dimensional systems, so it's not, say, easy. I mean, it's not so easy to implement them for the three-body problem, but one can do that, and one can prove that these invariant manifolds intersect transversally. Okay, so this is for the first, say, item in the list, and then I have 5 minutes, so I should go fast. Let me give some ideas on how to build this sequence of strips, as in the Smale theorem, to build a horseshoe. Okay. So that's our picture. So we have at infinity a disk of fixed points times, obviously it's not a product, but I mean it's a picture. It's invariant manifolds which intersect transversally. That's what we've seen. Obviously in this plane, to build these strips is very easy if you want. It's just following Moser. Okay, but now we have to take care of these other two directions, where the dynamics is extremely degenerate. Okay, so what do we do in these directions? So we use this tool that Marian explained yesterday that is called the scattering map. Okay, so what's it? What's that? So if we have a thermally hyperbolic invariant manifold lambda, here it's parabolic, but I mean, let's forget about that. That's not say important here. And assume that this manifold has stable and unstable invariant manifolds, which intersect transversally along some, along some homologic channel. Then, thanks to this intersection, we can define a map, which we call the scattering map, from this lambda to itself, which works as follows. We say that x minus is sent to x plus if the unstable leaf of x minus intersects the transversally, if you want, the stable leaf of x plus. Okay, so this map sends a point at infinity to another point if they are connected by an orbit which is heteroclinic. Okay, so that this map is, I mean, one needs to put more conditions, but anyway, I mean, this map is well defined, it's symplectic, and I mean, one can actually analyze it and even get formulas for it. So in this case, let me go here. Since we have different, different intersections, we can define two different scattering maps. And again, I messed up with the.
But I got confused. This stable and unstable manifold, which dimension do they have?
So infinity, I mean, has it's a disk, so it has dimension 2. Okay. So these in manifolds have dimension 3.
Okay, so they intersect not in a point.
No, they intersect in a disk, say, which is, I mean, in a set which is homeomorphic to infinity, to the base, and that's why it allows to connect different points at infinity in a sense. Yes, I mean, we say transversally. I mean, it's as transverse as it can be in a sense. So in this setting, we can define two scattering maps because we have two different intersections. One, we can get formulas for these maps. And these maps, one actually can prove that they are close to completely integrable, meaning that they basically rotate, okay? Which again, if you want to obtain, if one wants to obtain, say, hyperbolicity, having, say, being close to rotation, it's not helping either. I mean, it's very, the motion is very stable. However, what we can see is that since we have two of them, and they are, say, rotating around different centers, there's, I mean, one can find a good combination of iterates of these two maps so that one can create, say, hyperbolicity, okay? So that one has like one rectangle, and its image is well aligned and gets stretching and contraction as usual, and I mean, and the behavior, say, it's hyperbolic. Now, this is for the scattering map, and recall that the scattering map, it's not, say, true orbits of the map. I mean, it's labeling orbits which are homoclinic to infinity. So we want to use this information for the true dynamics of the model. So how do we do that? So that's the picture we had. So what we want to do is, as usual in say, Smith theorem, we want to put here a 4D rectangle, and we want to compute the return map, right? And typically, how is this done? Well, first we have what we call the global map, which captures the behavior close to infinity, sorry, close to the invariant manifolds, and then a local map which goes close to infinity, right? So one can see that actually this essentially, and I'm cheating a little bit, this global map is given by, I mean, input coordinates by the scattering map at first order. So what I've given before for the scattering map can be seen now here in the global map. And then one has to analyze the local map. I won't talk about that. I mean, and this has to be done through a high-dimensional parabolic lambda lemma. Okay. So putting all together and looking at the global map and at the local map, we can prove that a suitable high iterate of this return map, because we need to see, sorry, we need to see this, right? We need to iterate several times the scattering map, so now we have to iterate several times the return map, we can see that we end up having basically the same picture as in Moser in the pendulum planes, so to speak. And in the center direction, we have essentially the picture of what I've seen for the scattering map. Okay, so all this together, it creates this sequence of 4-dimensional strips, which are well aligned, which gives, say, a small horseshoe and gives oscillatory motions. And also, one can set up conditions to prove that that one gets actual conjugation and one gets hyperbolic dynamics. I'm over time, so I'll. Yeah, exactly. No, I'm done. So thank you for your attention.